Hello again. So last time we were looking at this proof system for derivability in a very simple logical calculus of implication. And we were finishing with a cliffhanger where we saw that it's easy to show that things are derivable, but what if I want to show that this is not derivable? So this says that A implies B implies A, which doesn't make much sense, right? Because why would A be true just because it implies some B? And before, for the less than relation, we saw that we can pattern match on the proof D. So D is our assumed derivation of this thing. And we saw that we could pattern match on it to see that it's impossible that it could possibly be anything. And that way we can show that things were not derivable. So let's see if we can do this here again. I'll pattern match on the D. And it starts off quite promising, right? So up here we had 4 different constructors, but Agda says that, well, you only have to consider these 2. So some of them are already impossible, but I couldn't see that all of them were impossible. But maybe if you look a little bit closer at what these subderivations are, then it will become clear that it's impossible. So let's pattern match on this D again. Okay, this wasn't clear yet, but maybe if you pattern match on the D one more time, well, could be an application, it says. Well, what about the first thing? Okay, it could be an abstraction. Okay, so it could be a hypothesis. Well, this looks like it's not going anywhere, right? Because we're just getting more and more cases the more we look at these things. So this is not a good way to make progress. I'm just going to comment that out. And the reason it doesn't work is because we have these kind of open-ended assumptions, abs and ap, right? Where to derive something like this, I can derive something of the same shape, but for a different A. So it's impossible to know that this is actually going to ever finish, because maybe there's another proof that's just a little bit bigger. So instead of trying to do this, we are going to define a semantics for our calculus. And then, so what that means is that we're going to define a model, and then we're going to show that every derivation here has an interpretation in the model, which then in particular means that if this interpretation is empty, then that means that it couldn't have been a derivation to start with. Right? So that way we can show that certain things are not derivable. But in order to get to that point, we need a little bit of machinery first. So this is another case study for how to use inductive families, but it's also good preparation for things later on in the course where we're doing things like this all the time. So the first notion we need is the semantic notion of a context, which is called an environment. And this, I'm doing this in a simple way. I'm just saying that an environment is a mapping from strings to sets. And the reason I need this is because I'm going to interpret my formulas as sets. But my formulas contain atoms, which are determined by these strings. So I need a way to turn these atoms into sets. So I'm just going to ask for an environment to do this for me. Okay, so that's the notion we need. And then here's the plan. I'm going to take every formula and turn it into a set given an environment. I'm going to take every context and turn it into a set given an environment. And then we're going to show that if we have a derivation and an environment, then that gives us a map from contexts to in the interpretation of that formula. So we assume everything in the context and we derive the conclusion in the formula. Okay, so let's do that. Let's start by doing the definition of the formula interpretation. So I'm given an A here, which is a formula, and I'm given an environment rho. And I'm doing this by just pattern matching on the formula A. So you see that it could either be an atom or it can be an implication. Okay, if it's an atom, then this X here is a string, and I'm just going to use my environment to look up what set this should be mapped to, because that's why I had an environment, right? And if it's an implication, then I'm going to just turn this into a agda implication, which is the same thing as a function space. Right? So this is A formal interpretation for row implies B formal interpretation with row. Right. So I'm turning this syntactic implication into Agda's notion of implication. Right. And now for the contexts, a context is either empty or it's a given context extended with a new assumption. And if it's empty, then there's no information in this, right? So I'm just going to turn this into the unit type. Whereas if it's an extension, then this should contain the information in the rest of the context and the information in this A. So that's going to be a product of something and something. And this is going to be a recursive call. With the same environment. And here I'm just going to use the formal interpretation of A again in the same environment. So this is why I need this interpretation to have access to an environment, so I can pass it on to this interpretation. Right. Okay, so now I've set up my interpretation, but now I have to show that I can also interpret every derivation as a function like this. Right. And I do this again by pattern matching on the D. Let me see if I have to do it for all the different ways we can derive things. To rename that. Okay, so here's where we actually have to do some work, right? So we are asked to provide something in the interpretation of A, given that we have this argument, which is something in gamma and then something in A. So that's going to be a pair like this, right? So we see that we have exactly the A that we want, and we are just going to return that A. So this is like using the assumption we had in the environment, which makes a lot of sense. Right. Okay, and here we have a weakened thing. So D is the derivation of A, and we have an extra B in our context. So this context is of this form. Right. So we see what we can do is we can just ignore this B and continue proving the soundness of D for the same row and with the first part of the environment, or the context. Okay, what about this one? So here we have to prove A implies B, and we have a derivation of B in the extended context. So if I look at that and do a recursive call, then that will give me a B of something. Okay, so also I want to derive a function, right? So I can do that with a lambda. Okay, it's a bit unclear exactly what it is. It's something arrow B, so that's what we want. Okay, and here I have to give an environment. I already have one. And here now I have to give the interpretation of my extended context. So it's something comma something. And here I need something in gamma, which I have. And here I need something in A, which is exactly what my function is giving me. Right. Okay, so that also seems to make sense, right? We interpret abstraction as abstraction, Agda's notion of abstraction, and we're also going to interpret this syntactic application as Agda's notion of application, right? Because what do we have here? We have to make an A, while D, if I interpret it using row and gamma, will give me a function which will get me an A. If only I could give it one of these. But E will give me one of these, right, if I interpret it. If I can type. This is supposed to be a gamma. Okay, and now the point is that we can show that this example is not derivable. And how do we do it? If I assume that I have a derivation of it, now I have to give a bottom. Well, if I now interpret my derivation in the model for some rho and some gamma, I don't know what that is yet, where I have to say what my environment is. Okay, so what I have here is something which is going to live in row of A. So if I say that row of A is empty, and I also have to say what row of B is, and I have to say what row of anything else is, which I don't really care about. Then I'm going to have something in row of A at the end, which I define to be empty. If only I can give these other arguments. So what do I need? Here I need something in the interpretation of the empty context. That's easy. Okay, and here I need something bottom arrows, whatever I interpret this to be. So if I take this to be top, for example, then here I can define this to be lambda don't care to tt, for example. And here I really don't care, so I can just use the natural numbers or whatever I want. Okay, so in the model I knew that I couldn't do this for any interpretation of A, so I just choose one where A was interpreted as the empty set, and then I could show that this was actually not derivable because of the soundness theorem. So this way you can use the model to show things that are not possible. Right? And soundness means exactly that everything that is provable, everything which has a derivation, is also true in the model in this sense. Right? And the converse of this is called completeness. If it's true in the model, then it's provable. And that's not the case for this semantics. This is a little bit too simple-minded, because if I just give you something which is true in the model, how can you know that? How can you find a derivation for it? So you need more refined notions of semantics for that. If you want interested, you can look up things like Kripke semantics.